In Chapter 9, we will study the problem of equilibrium. Now, earlier we covered equilibrium for a particle, and now we're going to study equilibrium when you have an object that can rotate. A body that's not a particle is said to be in equilibrium when two conditions are met. The first is that the sum of the external forces is zero. This is the same equilibrium condition we had previously for particles. It is called the translational equilibrium, although in the book by Giancoli, Physics 6th edition, he calls it the first condition of equilibrium, or the first equilibrium condition. That is very unique to that book. I've never seen that said in any other book. Generally, it's said to be the translational equilibrium, and what it says is that an object, if it's not moving and you were to sit there, you would not want it to suddenly start moving and taking off with some acceleration in some direction. So you want the acceleration of the center of mass to be zero. The condition for that is that the sum of the forces be zero. Now this is a vector equation. Vector equations can solve for more than just one unknown, because this vector equation can be expanded into multiple scalar equations. The second condition is that the sum of the external torques is zero. This is generally known as the rotational equilibrium condition. Again, Giancoli does this slightly different. It says this is the second equilibrium condition. As in the previous statement, that seems to be very unique to this book and not what you're used to hearing. So this one is equivalent to saying that the acceleration is zero. This one is equivalent to saying the angular acceleration is zero. So that's what we want. We don't want it to take off, but we also, if it's like a bridge or something, we don't want it to start accelerating. So consider this case. Here's a person driving on a bridge. The bridge has an X, Y, and Z coordinate system. We're only going to consider this to be a two-dimensional type problem, flat land. And there is an axis coming out of the board that you can think of as I put my pen perpendicular to the board right here. And that's the Z-axis. So there's three things we do not want this thing to do if Luigi here is going to get across this bridge without having trouble and not fall into the water below, which maybe has a giant shark or something. Dun, 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 dun. Well, in order for that not to have, we do not want this to suddenly take off this way. So we don't want it to accelerate. If it's sitting here stationary, we don't all of a sudden want it to take flying off upwards like a rocket. Those are the translational equilibrium. We also, of course, don't want the bridge to accelerate into the water with the shark. So that's the first condition, no acceleration. We also don't want it to rotate around. So we don't want this bridge here to suddenly just get up and flip over like that and throw Luigi's car over into a wall or something. That would ruin his day as well. So we want alpha to be zero. So a two-dimensional problem has three conditions, two forces, one torque, all of which must be zero. Those are the predominant problems that we'll work in this course. Now, in the real world, problems are more likely to be three dimensions. So our 2D problem, as I said, produces three equations, so you can solve for three unknowns. If it's a three-dimensional problem, you get more equations, even though you only have the two vector equations. The number of scalar equations they produce turns out to be 6. And they're the following. You don't want this three-dimensional cylinder to accelerate this way, so we need, let's say this is X, this is Y, and this is Z. You need the acceleration in Y to be 0. You don't want it to take off this way. You need the acceleration in X to be 0. You don't want it to accelerate upwards, so you want the acceleration in Z to be 0. You likewise don't want it revolving around the x. You do not want it accelerating this way. So we need alpha of y to be 0. You don't want it to be rotating this way though either. So you want a sub x to be 0. And you likewise don't want it turning this away. So az is 0. The conditions for the 3 accelerations of the rotations are here. This is the one for alpha y, for instance. The 3 accelerations for the translational acceleration are right here. This, for instance, is ax equals 0. So those are the conditions to solve an equilibrium problem. And you can sometimes, and most of the time, leave these equations alone, but this may not be the best way. Now, what's usually done is that an engineer or such wants to find some of these unknown forces used in this equation. When they do that, there's a name, it's called statics. So it's an equilibrium problem. Sum of the force is 0, sum of the y's equals 0, sum of the torques equals 0. But when you solve for one of those forces, they call it statics. And generally in engineering curriculums, early on, they have a couple of courses, or at least one combined course called statics and dynamics. Dynamics is when the a's and the alphas are not 0. We've been doing that. Statics are when they are 0. Another useful fact to know sometimes is the fact that you can only get 3 independent equations in the 2D problem, but that doesn't mean they have to be 2 forces and a torque. If you have a bridge or something like this, and you have a bunch of forces, F1, F2, F3, F4, F5, so forth. You may either solve for the sum of the forces in x and y and 1 torque, or you might, for instance, say the sum of the forces in y is 0, but decide to calculate the torques about this point, sum of the torques about P be 0, and then turn around and solve the sum of the torques over here, which might be called point B. You still have 3 equations and can solve for 3 unknowns. It turns out, how do you know that that'll work? If the sum of the forces is equal to 0, as we're requiring for an equilibrium position, and if the sum of the torques is 0 about an axis, as we were requiring for this problem, then we are guaranteed that no matter which axis you choose, take any place, take out here, take out here, no matter which axis you choose, purple, red, or green, the sum of the torques will be 0 if there's 0 about one of them. So if you find it's 0 here, it's also going to be 0 there. It's also going to be there. Giancoli likes to say that the choice of the axis to calculate the torques is arbitrary. The nice thing about doing a torque is that when you do a torque right here, this force does not create a torque. This force does not create a torque. Therefore, they don't show up as unknowns in my algebra. You can simplify your equations and save considerable algebra by a wise use of calculating a torque. All right, in the next video, I'll show you how to actually do some problems.